Okay, let's get started. I am, of course, basically going to do the lecture that I was going to do on Monday, because Monday I ended up basically reviewing stuff from the week before, doing that problem and explaining different things about work and energy. So we've already talked about this wonderful picture. We've already gone through and solved this problem. When I solved this problem, I started working it and then I stopped because I realized, you guys are learning. Seeing a problem work, but not having an explanation for the thought process is not really all that beneficial to you, because on the test, the physics of that thought process, that's what I'm looking for. That's what I want the students to develop. So remember, in solving this, I sat down and I first identified, okay, this is going to be a problem where I use the things of collisions, the relationship between energy and momentum for a collision. And so we had, before the collision, we had a car skidding, then there was friction that was creating a non-conservative work, and I used the work-energy relation to relate the speed of the car before it hit the brakes to the speed after the collision. During the collision, because the collision is short duration, we said that momentum should be approximately conserved. And so I used conservation of momentum to relate the two speeds of the cars before the collision to the speed of the cars sticking together after the collision. And then, sorry, it's taking me a second here to find. Hope I put down the right line. Nope, I didn't. And then when they skid together, I once again had the work-energy relation to relate the final speed, stop, to the speed that they started after the collision. And so I had to go through going from initial braking to collision, work energy. During collision, conservation momentum. After collision until they stop, work energy again. And I had to do all three of those to solve it. So understanding how to put those pieces together, that's what we're trying to see you do on the test, right? We're not looking for people able to put numbers into problems. So that's why, on those last 5 problems, I want to see the figure. I want to see you describing the process, the thought process that went into it, and then the equations that go with that thought process. And that's, 70% of your score right there. And then the last part of your score is actually doing the work. So with this problem, we have 2 clicker questions. Question number 1, what type of collision was involved with the cars? So we had car 1, car 2, going not as fast, becomes car 1 and car 2 mashed together. What type of collision was that? And of course, the person I'm going to call on is going to have to describe what that collision type means. Okay, I still have quite a few who haven't answered. Eric, Leslie, okay, Brian just did. Jeff. So Eric, Leslie, Jeff. Now it's just to Leslie. Is Leslie not here? Okay. Then I won't wait for Leslie if she's not here. Okay, so we had 0, 1, 0, 25. There's Leslie. Okay, so all but one person went with inelastic. Arlene, chances are you went with inelastic. Is that correct? I would feel really bad if you said, no, why did you go with an inelastic collision? Okay, that is indeed the perfect answer. They stuck together. That's completely inelastic. So it was an inelastic collision because they stuck together. Next question, which concepts, and there are more than one involved, do you need to use to solve for the initial speed of car 1? We're going to have a whole bunch of people who answer on this one. So this one's multiple answers, so you put in all the ones that you believe are correct, and then you hit enter. I just want to make sure Trace gets his exercise during class. Okay, people who haven't answered: Arlene, James, Christian, Augusta, and Erika. Okay, I'll give it another 10 seconds and we will move on. Okay, moving on. We had 1, 14, 7, 5, 20, 7, 11, 22, 5, and 0. Okay, so, Erika. No, you got the best position. Choose the one you have the most confidence in. Which one?
Because the cars, because they're driving and they're stopping, so there's friction involved.
Okay, perfect. There was indeed work done by friction that we had to consider. Next up, Peter.
I think Newton's second law because we're looking for the initial force.
It's actually not looking for the initial force. In order to find, okay, I can live with that. In order to find the force of friction, which you need for the acceleration, you have to use Newton's second law. Because you can't find the force normal without Newton's second law, and you don't have the force of friction without the force normal. Okay, next up is Becky. She knew she was going to be in the first half. So what you got, Becky?
H.
H. Conservation of momentum. Why? Why not? It's not a good answer.
I honestly don't know.
Because during the collision, momentum was conserved. Okay, next up is Alex.
I did F, work energy relation, because to find the initial speed, you need to take the work done by friction.
Nice.
Final speed when it hits the other car.
Okay. I'm going to put while skidding because while you were correct, it also was before the collision. One of them was skidding, so you got it two places. Right? Because you said after the collision.
No,
Okay. Well, you have it two places. That's why I used the general. Oh, now life is getting harder. I will help you out at this point and not call on more people. Nobody gets to do the more than 1 second half on the cards. Newton's first law. What is Newton's first law, right? We do have a test a week from yesterday. Newton's first law is certainly something you're going to see on the test. What is Newton's first law? That's actually the first law of thermodynamics. It's still the first law. Okay, it's the law of inertia. An object stays in constant motion unless something acts on it. Now, in this case, we know the car didn't stay in constant motion. We know something had to act on it, but that didn't help me solve it. So it was going on here, but it didn't help me solve anything. Newton's third law. What does Newton's third law say? For every action, there's an equal and opposite reaction. So something's putting force on it. Object A puts force on B. Object B puts equal force in the opposite direction on A. Certainly in a collision, car 1 is putting a force in car 2, car 2 is putting an equal and opposite force back in car 1. Those forces were internal. Didn't matter to us. We could have said, okay, well, but when we talk about force friction, I might have calculated the force, that the tire is putting on the earth, and then you use third law to go from that to the force the earth is putting on the tire. You can think of it that way. One could defend, okay, there's a way to use the third law here. Work done by gravity. That is an absolute negatory. Why is there no work done by gravity on this? Right. It didn't have any change in vertical height, and work is force times distance parallel, the motion parallel to the force. So if we had gravity is vertical, there's no vertical motion, then there's no work done by gravity. Not part of our solution. Conservation of energy. Conservation of energy is true. That's the first law of thermodynamics. But we didn't use it here. We had energy that went from kinetic energy into heat. If you feel the tires after a car skids, you'll feel that they're hot. That is a place where some of the energy went. Also certainly into sound, also into bending metal. We had energy going all kinds of different ways. Total energy was conserved, but we didn't calculate anything about the heat generated or about how much energy was used to bend the metal. So we didn't use conservation of energy. Conservation of mass. It used to be that people thought mass was conserved. Now we know there is no such thing as conservation of mass. Mass is not conserved. How many people are a little shocked to hear that? Only one person raised their hand. It wasn't until 1905 when Albert Einstein came out with his theory of special relativity that we come to the very bizarre, I think it was in his special relativity that he came out with a very bizarre idea that mass is simply a form of energy. Energy can't be created or destroyed, but you can convert energy into mass or convert mass into energy. So mass is just not conserved, and conservation of distance was a nonsense answer. I'm glad nobody went for the nonsense answer. Distance isn't conserved. Okay, so there, when you're doing your physics, you're thinking about what applies here. Now, I could have put kinematic equations on here. You might have used kinematic equations to solve this. You could have used Newton's second law, found the acceleration, which I think is what Peter was saying. Once you find the acceleration, you use kinematic equation to relate distance, acceleration, and speeds. So you could have used kinematic equations as well. Shifting gears completely. On January 13, there was an editorial written in the New York Times that said, and you can read the whole quote here, Professor Goddard, with his, quote, chair, end quote, in Clark College and the countenancing of the Smithsonian Institution, does not know the relation of action to reaction. What is that? Action to reaction. What is he talking about? Newton's third law. He's saying Professor Goddard doesn't know Newton's third law. That if you're going to have something push on you, you have to push off of it. And so rockets can't work in space. Now, we all understand that's wrong. But he said that, of course, he seems to lack the knowledge laid out daily in high schools. Up until around 1900, scientists thought that there was some kind of material out in space. It wasn't a vacuum. We know we can't have sound travel through a vacuum. And so they assumed that nothing can travel through a vacuum. So for light to travel from the sun to us, these are having some medium for it to go through. And so they called that the luminous ether, the famous ether theory. And so up until that point, people would have accepted that a rocket could have worked out in outer space because the rocket pushes stuff out. They would have said, oh, that stuff is going to hit the ether, and there would be then a force pushing back and make it go. When they said, no, there is no ether, then this wise fellow said, Goddard is wasting government money by suggesting that we can make a rocket that works outside the Earth's atmosphere. They published this retraction on July 17, 1969, one day after the Apollo 11 mission left Earth and went into outer space, as we call it, and used a rocket on July 17 to readjust its trajectory in outer space, in vacuum. So at that point, it was really clear that Goddard was right and the editorial was wrong. So what makes a rocket go if it's not Newton's third law? If it's not, it pushes something out and that thing pushes on something that pushes back. What makes a rocket go? I know the 6 of you and 252 we already, or 251, we already talked about this. So for the other people, what makes a rocket go?
Because it already has motion when it gets there and there's no friction stopping it, it just keeps going.
Okay, inertia will keep it moving. Now you also have gravity. You might not realize this, but like if you're at the International Space Station, the force of gravity on you is like 80% of what it is when you're standing on the surface of the Earth. So there is a reasonably strong force pulling toward the Earth. It stays in orbit because it's moving tangentially, and you have to have acceleration toward the center to make it change directions in the same circle. So we say they're constantly flying toward the Earth. But no, that's not what makes the rocket go. It would keep going because it's not what makes it go. So like I said, on July 17, they did a burn to change the orbit out in the vacuum of space. So they changed the orbit that wasn't inertia. So how could they change the orbit? Internal forces. Okay, he says internal forces. Kind of. So I'm going to take what Irving said and work with it. You have Newton's second law that says the net force is mass times acceleration, right? Kind of. The true equation for Newton's second law, which I mentioned, is that the net force is equal to the change in momentum divided by the change in time. And so the rocket, I'll write this up here, force net is equal to change in momentum over change in time. So the rocket has fuel in it, and it burns that fuel. When you burn something, you have an exothermic reaction. A rapid exothermic reaction, that's the definition of burning, right? So that rapid exothermic reaction makes the molecules really hot. High temperature is another way of saying high kinetic energy. Temperature is a measure proportional to the average kinetic energy. So suddenly you have these molecules moving really fast. And then you put a nozzle on them to direct them all in one direction. So those molecules, before you burn them, they were stationary with regards to the rocket. Then they're moving out really quickly in that direction. So those molecules had a change in momentum in that direction. But if the momentum of the rocket and its field is conserved, what does the rocket have to do in response? It's going to have to accelerate in the opposite direction so the total momentum stays constant. That's what makes the rocket go. So, you talk about the internal force. When you push the gas out, that gas is pushing the rocket forward. It doesn't have to hit anything for that to happen. So that's how a rocket works. We have two equations for rocketry, and you're going to use both of them for one of the homework problems tonight, right? So in the calculus class, we, of course, worked through these problems and how we get the equations. For you without calculus, the acceleration, if you have gravity, the problem tells you that you are out in outer space where there's negligible gravity, so the g will just be approximately 0 there. Then the acceleration is equal to the speed that the exhaust leaves the rocket divided by the mass of the rocket and then multiplied by the rate at which gas is leaving the rocket. So how many kilograms per second is leaving the rocket. That minus g is if it's on Earth going up and you have g down, then your total acceleration you have to take into account such gravity. On your homework, you just won't have g. So the acceleration will increase if you have a faster ejection speed. It will increase if you eject more mass per second, and it will decrease if you have a heavier rocket. So one of the things with rockets is they want to try to make the rocket as light as possible so they can get the biggest acceleration from it. Now the other equation is calculating the final speed. And I was talking to Keith Reese, and he said that he didn't get to these equations. How many people are unfamiliar with the mathematical LN? I know I asked this way, and then people just embarrassed. How many people are familiar with it? Okay, so we don't have a problem with the natural log function. It turns out that when you integrate something that is, the rate is dependent on the size, you get an exponential, and the natural log is the inverse function of exponential. That's where it came from. So the final speed is equal to the speed that you have your exhaust leaving times the natural log of the mass you started with divided by the mass you ended with. If you end with 0 mass, your final speed goes to infinity. If you can burn up the entire rocket except for one atom, that atom will be approaching the speed of light in its speed. What are the chances that you can do that? 0, of course. But if you can make this here is the final mass of rocket, and this is the initial mass of the rocket plus the fuel. So if you have the fuel is a significant fraction of the total mass of the rocket, you will reach a much higher speed than if the fuel is a minor fraction of the rocket's mass. And so you're going to use both of these equations in one of your homework problems. Putting the numbers in is pretty simple. They give you the burn rate. They give you the change in mass over change in time. So you just put one number in for delta M over delta T. And then, of course, they give you the other numbers as well. But I saw somebody who was trying to figure that out, how does that fit into it? So I'm not even going to do a problem with it. It's just one problem so you can have some exposure to rocketry. Now we're going to get into actual equilibrium. Equilibrium, what is it, Latin? What does equal mean? Like Equifax. Equifax. What does the equal mean? Means what? Is the same? The same. Okay. Yes. The same. So I was just looking for equal since it's so close. So equal, the same, Equilibrium. Anyone got familiarity with that word? What? Okay. She said balance. You're thinking of like the Libra or Statue of Liberty holding the balance. Well, actually, that means force. And so when we measure pounds, what's the abbreviation for pounds? LBS. What does that stand for? Yeah. It stands for that, for the Librams. So equilibrium is equal forces. That's what the words mean. In practice, it has two pieces to it. Not just some of the forces is zero, that would be equal forces, but also some of the torques is zero. So now we have a new concept, torque. You know, like, man, I'm really torqued up about that homework. Not the way we're using it. Torque, I go back to when I was a kid. I was like 7 years old. My dad's talking to my uncle, Jack Webb, but not famous. And Uncle Jack says, yeah, that car's got a lot of torque. And his little Richie's like, yeah, what is torque? My dad said, tiny amount of twist the engine has. And little Richard says in his head now, yeah, he doesn't know what torque is. That's a stupid answer. But it turns out my dad was right. Gotta have more faith in the old man. So, given my age, that's probably how a majority of us should use. Torque is the rotational equivalent to force. So forces are things that push or pull and result in acceleration. Torques are things that have a rotational push or pull and make things accelerate in rotation. So if I take you as an arm and I twist on it, I put a torque on it, right? Of course, I didn't twist on enough to hurt her, right? Shoot. All right. So, a simple example. If I take this and I hold it above my head, is it making my arm try to rotate? I have it perfectly balanced here, so it's not. It would say it's equilibrium because it's not making it rotate, at least in terms of the torque. So I put it out here, is it trying to make my arm rotate? Absolutely. At what angle is it hardest for me to hold this? Straight out here. So you've got some idea of the torque thing. Now let's get to some mathematics of it and the explanation. So torques are forces that are going to make things rotate. They start with a force, and I, of course, got ahead of myself. The equation for torque, okay, so this is the symbol we use for torque. That is a tau, Greek letter. Torque is a vector, it has a direction. And torque is defined as R cross F. How many people have done a cross product recently? I expect 6 hands to shoot up because I did them in class yesterday. Cross product means, notice, that would normally mean multiply to people. That cross means multiply. With vectors, a cross product is called a vector product or a cross product. Either one is sufficient. It is multiplying perpendicular parts, and it has a direction to it. Now, right now, I'm only going to focus on the perpendicular parts, and then we'll get to the direction in 10 minutes or so. So the example of me holding that mass, if I was holding it straight out to the side, I look at the mass here. That was 5 kilograms I was holding in my hand. So what force was that mass applying to my hand? Okay, force of gravity, that is mg pointing down. If we multiply it out, 5 kilograms times 9.8 meters per second squared, that was 49 newtons pushing down on my arm. Or how many pounds? The acceleration of gravity is roughly 2.2 pounds per kilogram. Really odd looking unit, but that would be the acceleration of gravity. So if I have 5 kilograms times 2.2 pounds per kilogram, that would be about 11 pounds that I'm pulling out here. I think it's easy to hold 11 pounds out here. Thank you, because it's not. So my arm was trying to go down. Now we could take a meter stick and say that my arm, from the pivot point here in the shoulder out to where I was holding it, is 70 centimeters. So I take my distance of the arm, (70 centimeters), and then I can calculate the perpendicular part. Now, if you look at this, we put the r vector is the vector that goes from the pivot point to where the force acts. And that's perpendicular to the force vector. So if I multiply the perpendicular parts, I get the torque is the force perpendicular times the radius is 49 newtons times 0.70 meters. Notice I switched it to meters. And so that is 49 times 7. Well, 350 minus 7 is 343. 34.3 newtons times meters. Notice the unit. Newton times a meter. Newton is force, meter is distance. Oftentimes you'll see in America, this engine puts out X amount of foot-pounds of torque. Foot, distance, pounds, force. Those two together make torque. What else have you seen that has units of newtons times meters? Joules. 1 joule is 1 newton times 1 meter. You never, ever list a torque with units of joules. Joule is reserved for energy. So it doesn't just mean newton meters, it means energy in newton meters. So torque is, you just write newton meters. We don't have an abbreviation for it. What's the difference in torque and work? Work was equal to force dot distance. The dot product was the parallel portions. The cross product was the perpendicular. So they're both a force times distance, but the vectors, the directions, make all the difference between work and torque. Now, going back to one last thing before we move on, if instead of holding it horizontally, of course, I don't need this arm. My arm is going to be, if my arm is something like this, at an angle of 45 degrees, I have the same length of my arm, but now R is going this direction. I have the same force of gravity. What is the torque in this case? I need the perpendicular parts. How much of this radius is perpendicular to the force of gravity? The what? With the angle that I wrote, it would be cosine theta. If I had written that angle, then it would be sine theta. So you have to pay attention to what angle it is. The angle that we usually use is indeed this angle, the angle between the radius and the force. And so in that case, the perpendicular distance is going to be 0.70 meters times the sine of 45 degrees. And so that's going to be 0.707 times 34.3. I don't know. I really don't know what that number is. What? Now, we only had two significant digits, so it was really 34 and 25 for the numbers, but I wrote one extra. So there you can see the torque is bigger when it's straight out here because my radius is perpendicular to the force. When it's up here, it's a smaller torque because the radius is not perpendicular. Only the perpendicular part of the radius matters for torque. So the answers that you all gave me about torque were correct, but now we have mathematical relationships to put them together. Okay, coming back to the order of this. The two conditions for equilibrium. Sum of the force is 0, the net force is 0, and sum of the torques is 0. Now notice those are vector equations. So sum of the forces is 0 can be broken up into sum of the forces in the x direction 0, sum of the forces in the y direction 0, sum of the forces in the z direction 0. So you get 3 equations from that. And likewise, because torque is a vector, you can get 3 equations from that. So those 2 equations represent a whole of 6 equations that you can use in solving problems. And I know it thrills you to hear in solving problems. But we'll solve some. I find them fun. Of course, I find physics fun. I find solving problems fun. I find tests exhilarating. Man is standing here. Akimbo, right? That's what we call it, the hands on the hips. So he's standing there, and if I were to ask you, is he going to fall over? You would answer, shouldn't. Not unless he's some clumsy person or whatever, has a sinkable episode. So he's standing here, he's in equilibrium. Now, if I'm standing here and I'm in equilibrium, let's say, of course, I'm absolutely tired of me using him as an example. So he comes up and he gives me a shove on the shoulder. Come on, give me a shove. A shove this direction, not backward. Push me out. So he pushed me out. I tipped up some, but I came back. We would say that was a stable equilibrium because I returned after I've been displaced, I returned. But let's say the force was really angry. So he gives me a hard shove. I can put my arm down so he don't elbow you. So he gives me a hard shove. Okay, so there, I fell over. He got me out of my stable equilibrium. You have the same thing with things like a dresser in your house. The dresser should be equilibrium, shouldn't fall over. But if you push it hard enough, you can tip it over. You can get it out of equilibrium. So let's talk about what makes that. When you have something that has the center of mass, that's to take the average position of all mass, and it is within the base, then if you tip it, that center of mass is going to have to go up. What happens to the energy if the center of mass goes up? If you take a mass and you raise it, the energy goes up. Well, things naturally want to go to the lowest energy available. So you raise that center of mass, and as long as you're within your base, it'll fall back down to get it back down to its lowest position. But when he hit me hard enough, when he gets me up to my center mass is over my foot, then I'm precarious. And if he moves me more, I'll just keep falling that way. My mass can fall to a lower level. So it was in a stable equilibrium like this, unless he pushes me far enough to get so the center of mass is not over my feet. Now we could take this and we could apply it to the Leaning Tower of Pisa. The Leaning Tower of Pisa, okay, that's clearly exaggerated. If the Leaning Tower of Pisa was like this with the center mass right here, and here's the base, would that be an equilibrium? No. This here is outside of the base, and that would fall down. Now, the reality of the Leaning Tower of Pisa is something like this with the center mass about here. So the center mass is just barely inside of there, so it's still stable. But if it tips a little more, then it would become unstable. Why does all this happen? Well, we've got something like this going on right now in San Francisco. They built this super expensive high-rise apartment complex, and it's settled by, a couple feet on one side. And so you have a situation where it's settling because you have different people blame, people who build it blame the subway. The city says, no, the subway's too far away. It's not the subway's fault. But the ground was not stable. The ground sunk underneath it. That's what happened to the Leaning Tower of Pisa. It was built not, where's the wise man build his house? Upon the rock. Well, the Leaning Tower of Pisa was not built upon the rock. It was built upon the sand. And it's settled. And so they have undergone, I think it's 2 different construction projects to try to beef up the ground underneath so it won't go down anymore. They've actually jacked it up and then put stuff under there so they keep it in stable equilibrium. Okay, so we have stable equilibrium. If you displace it, it will come back to where it was because you have the center mass within the basis. Unstable, if you displace it, it'll go away and won't come back. There's one more. If I take this remote and I push it sideways, it just comes to a new equilibrium in a new spot. That we call a neutral equilibrium. So there are 3 types of equilibrium. Stable equilibrium, unstable equilibrium, and neutral. Stable equilibrium will return when displaced. Unstable will go away. And neutral will just find a new equilibrium. Now, torques, I've introduced it, but I want to wait. Here you can see pictures for what I just talked about if you want to come back and look at them. Let's just go to these questions and then talk more about torque. Which situation is or are, so there could be more than one, you have to enter the answers you believe are correct and hit enter. In equilibrium, a car parked on the side of a road, a car accelerating up to freeway speed, a car driving on a straight freeway at constant speed, or a car rounding a corner at constant speed. Okay, we're filling in. Waiting for Ashley Corso, Arlene Leslie. It says you have not answered. Now it's just Arlene and Leslie. Okay, Leslie's in. And Arlene's in. All right. So we had 28 people that said the car parked on the side of the road. And we had 27 that said a car driving on a straight freeway at constant speed. And 1, a car rounding a corner at constant speed. Christian. There were 2 correct answers. The 2 that have almost complete unanimity here. Why was a car rounding a corner at constant speed not correct?
Because change in direction.
Change in direction means that there had to be an acceleration and hence a net force. Perfect. So even though it's at constant speed, we have our condition force net equals 0 that's necessary for it to be in equilibrium. If it's going in a circle, it's changing direction, which means it's accelerating, so the net force ain't 0. Perfect answer. Now to the direction for torque. We did the calculation for torque. Wasn't that hard. The direction is new and bizarre to most people. So we determined the direction for a torque using what we call the right-hand rule. Did I talk about the right-hand rule in this class? Yeah, I did. So with the right-hand rule, you only use this with the cross product, and your index finger is the first item in cross product. Your middle finger is the second item in the cross product, and then your thumb is the direction of the answer. Now I'm going to add some decorations to this. I'm going to put vector signs over these. Vector signs were not over this equation from a slide that I don't remember where I got from. I did not make this. Don't want to be accused of plagiarism here. They did put vector signs over because it's in bold font. If you don't have vector signs, that cross means multiply. If you have vector signs, it means a cross product. It has a different meaning. So it is absolutely vital that you have vector signs or you have a different meaning for the equation. And so if we take my example of me holding this out here, the first item for the torque cross product is R, the radius, and I said the radius goes from the pivot point to where the force acts. So you take your right hand, and I would like you to do this with me, well, until I get tired. Take the index finger of your right hand and point it in the direction from my shoulder to where the mass is. Okay? Then, the middle finger, you keep your finger pointing in that direction. Of course, I have my left hand here, so holding my right. Rotate your hand so your middle finger can point the direction of the force, which is down. Okay, so your index finger should be pointing that way, and then middle finger pointing down. What direction is your thumb pointing? Toward the back of the classroom. Thus, the direction for the torque that this mass is creating about my shoulder is that direction. It's perpendicular to both the radius and the force. And so you're going to have to do this not on this test, because this test will be ending with the work energy stuff. But on the next test, you're going to have to, is the work energy stuff? Yeah. On the next test, you're going to have to use the right-hand rule to determine the direction of a torque. So let's just see if I have, I don't think I do have another, a clicker question. We'll end the day with this clicker question, and then we'll, of course, do more stuff with this on Friday. Suppose you hold the weight out to the left side, this way. With your left arm straight, what direction is the torque created about your shoulder by the weight? With your left hand out there, it's easy because then your right hand is free to do the right hand rule. So you're holding it in your left hand, holding it like this. Okay, everyone but Jeff and Arlene has answered. Arlene. Okay, because of time, I need to go on. Okay, so we had 4 answers that were given. Because of time, I will just say it's to your rear side. You would take your right hand, index finger points from the pivot point to where the force acts, middle finger points down, thumb points to your rear. To find the magnitude, when I put the absolute value sign, that means magnitude. You take the radius times the force times the sine of the angle between those two vectors. Okay, I'll see you on Friday.